All right, so we're going to get session 3 started. Our first speakers are Mark Simkin, who's a researcher at Flashbots, and Mateusz Morusiewicz, who is a research engineer at Flashbots.
Okay, hello. So I'm going to talk about a new protocol for anonymous broadcasts. I'm going to roughly define what this is and kind of like why this protocol has an interesting point in the trade-off space, and kind of explain a high-level idea of how the protocol works. And then Mateusz is going to explain, all the practical side of things and how fast it actually is. Okay, so just to kind of like get on the same page, in the anonymous broadcast setting, we have a bunch of parties, and they all have a message, and then they would like to interact in some way over the network, and at the end, kind of like the network all together should learn what were the messages, but you would like to hide who sent which message, okay? And in particular, you would like to have the property that even if some of the participants in the network are corrupt, or even a lot of them are corrupt, then the honest parties have full anonymity among all the other honest parties. Okay, so if there's 100 parties and 70 of them are corrupt, then if you see an honest message at the end of the protocol execution, it should be still completely unclear which of the 30 parties sent which of the honest messages. That's the ideal guarantee that we would like to have. And ideally, we would like the protocol kind of like to work even if some parties misbehave, if some parties don't send messages, if they try to attack the protocol and prevent it from proceeding. We would always want that the protocol actually terminates as good as kind of like, theoretically possible for some corruption thresholds. And yeah, as I said, full anonymity. Kind of like, okay, so this is like from a functionality standpoint, what we want, what are the inputs, what are the outputs, kind of like what are the efficiency metrics that we care about. We would like to tolerate as many as possible corrupt parties. So the more we can tolerate while the protocol still functions, the better it is. We would like to minimize latency. So from the point in time where I decide to send a message over this anonymous broadcast channel to the time where the message gets delivered, I would like to have as little as possible latency. And ideally, I would like to minimize the bandwidth overhead as much as possible. So a single execution of this anonymous broadcast protocol should not create a disproportionate amount of traffic on the network. Usually you can't have all three in the best possible sense, so kind of like, you have to pick your poison, and different approaches pick different poisons. So onion routing in a very high level, in a toy version of the problem, kind of basically has a client and there's a bunch of servers. Some of the servers might be corrupt, and what the client does is it picks a path through this network, and then kind of like one of the service in the end basically reveals the message. And this is like a toy version. Obviously, there's like much more sophisticated things happening in practical onion routing approaches like Tor. But one of the issues that you kind of have to, one of the advantages that it has is that it has very small bandwidth overhead, computational overheads, because I just send the encrypted message and I just forward it a few times. It doesn't really induce much overhead over just sending the message. But it has potentially high latency. Depending on how you exactly deal with this is not always clear. Like you might do it via kind of like, a financial argument about the capabilities of an adversary, or you kind of like, if you don't do that, well, then you need a lot of hops in your network to be sure that some of them are honest, and then you end up with a high latency solution. And this can potentially lead to weak anonymity guarantees. If you're not careful about what you're doing, if, for example, if you make the hops too small and like your financial argument ends up not being entirely correct. A different approach is mixed nets. So here I have multiple clients, and they speak to a sequence of servers, and each server kind of like permutes an encrypted set of those messages. But again, kind of like this approach structurally kind of like has the property that like servers tend to speak one after another, increasing latency. So this is kind of, again, there's lots and lots of research that I'm sweeping under the rug here, but structurally this is kind of like a thing that these approaches are susceptible to, that like, I need a lot of hops for a mixed net. But they provide very strong anonymity guarantees, which is kind of like the strong suit. And the bandwidth overhead is moderate, kind of like, because I need to kind of like permute all of those messages, send them, permute again, all of those messages, so there's like, a moderate overhead in terms of bandwidth. So what do we do in our approach? Well, kind of, we pick one point in the design space, and we kind of like, we don't claim that this is the ultimately best protocol for any application, but we claim that like, it is interesting for some use cases where we optimize certain of those properties. So what we do here is we basically say, okay, we would like to have kind of like a maximum level of privacy and anonymity, in the sense that like we would like to tolerate as many corrupt parties on the network as possible, and we would like to provide as strong as possible anonymity guarantees for the participants. We would like to minimize latency in the sense that from start to end, we don't want to have many network hops. And kind of like the price we pay is that we accept kind of like a moderate bandwidth overhead. So kind of like compared to other protocols, we need to send more data over the network. But as we show that you can actually still make this work and you can get like decent practical performance with this approach. Okay? And in terms of the security of our protocol, we do kind of like something that I think is interesting in the sense that the liveness of our protocol relies on the security of TEs. So we assume that TEs kind of like are not broken for the protocol to proceed in producing output messages. But importantly, anonymity does not. So if it were to happen that we're wrong and somebody can break a TE, then it might kind of like happen that a denial of service attack is being performed on the network, but no one's anonymity is affected by this. Okay, so this in some sense makes TEs something like a falsifiable assumption. Okay, so I'll explain on a very high level how the protocol works. So we have 3 parties here, and they have a message A, B, and C. And the first thing that they do is locally put this message in a random location in an array. Okay, so Alice generates a long array, which is 0 everywhere, and then it just places the message A at some random location here. And on a very, very high level, ignoring all of the cryptography, at the end of the protocol, the parties will learn the sum of those arrays. Okay, so these are vectors, and I can compute their sum. And then, because the parties put their messages in a location that is independent of which party they are, I can see the messages, I can extract them from this array, but I don't know who sent what, okay? And now the main challenge in kind of like designing such a protocol is, well, how do I make sure that kind of like I have a protocol that only reveals the sum of these arrays without revealing any other side information? And on a high level, what we do is we use a technique from secure computation, which is called secure addition. And if you do it component-wise, then it's like secure vector addition. So the idea here is we have some servers. So we have some clients and some servers. And we assume that the clients run in TEs. And at least, for example, one of the servers is honest, where this is like a configurable parameter, how many servers need to be honest. What we again do is now each client encodes their message into an array, now just like abstracted away by these little differently colored blocks. And now we do something called secret sharing, where each party locally splits their array into a secret sharing of their data and provides one share to each of the servers. Okay? And now what the servers do is they have all these shares, and then locally add the shares that they received. And secret sharing is a primitive that basically says, if I have enough of the puzzle pieces, I can reconstruct the original data. If I don't have enough of the puzzle pieces, then I don't know anything about the data. And here we use secret sharing schemes which allow me to kind of like homomorphically add secret values. So the servers can homomorphically compute the sum of those different arrays and combine the shares to get the output. But this is kind of like good on a high level, but unfortunately these arrays need to be kind of long because, well, if I have n clients, this array length needs to be proportional to n. And now if I have k servers, then I kind of like need to send n times k amounts of data because kind of like each share is as big as the secret. So this is something that would make the protocol very slow. And we also didn't deal with the fact that servers might be malicious. They might just send the wrong message. So I'll explain how we deal with the bandwidth overhead here, and I'll just outline how we deal with kind of like the malicious server situation. So the idea is kind of like instead of secret sharing the data, we'll encrypt the data or these data arrays with some key that we pick ephemeral at every execution of the protocol. And now what I do is rather than secret sharing the data, I secret share the small key. And before I did the secure addition thing on the data, now I do the secure addition thing on the key itself, which means that I need to duplicate the key and send it to multiple parties, but the key is very small compared to the data, and all those encrypted ciphertexts, I'll just publish them on the network once, rather than server many times. And we use a special type of encryption scheme that has the nice property that if I take a bunch of ciphertexts, encrypt it under different keys for encrypting different messages, and I just compute their sum, then it happens to be an encryption of the sum of the messages under the sum of the keys. And because the servers helped us compute the sum of the keys without revealing individual keys, we can then kind of like use the keys together with this sum of ciphertext to recover the plain text array and from which we extract the messages. So this is the protocol on a very high level. And the main benefit here is really that like the secret sharing is the thing that is like communication expensive, but we only do it now for the small keys rather than the big message arrays. So there's a bunch of details that are obviously omitted in this protocol. For example, how do you deal with malicious servers? Like, a server might not produce the correct output, but what we show is that like if you construct a certain type of additive vector commitments, then the clients, in addition to secret sharing their data, they commit to the shares. And now when the servers speak, they basically not only reveal their message, but they also produce a corresponding opening where I can check, is the server's message the correct message or is it the incorrect message? And kind of for now, I just said, well, the parties individually place their message in a random location in the array. Messages might collide, and at that point, kind of like I compute their sum, so it's not clear how I extract the message. But it turns out there's various ways to deal with this, with different trade-offs in terms of like how fast do I do the encoding into an array, how big does the array need to be compared to the number of clients. So one approach is to use something called invertible Bloom lookup tables or filters. Another one is to use something called Newton-Girard identities for polynomials. And finally, kind of like, even though kind of like this protocol tries to minimize the bandwidth overhead overall, still sending all those ciphertexts is the main bottleneck. So there's different approaches of how you can mitigate this as well. So rather than sending each individual ciphertext to each party, you might think of having aggregators who kind of like act as fully untrusted intermediary nodes that aggregate the ciphertext and then forward them. You might use some erasure coding tricks of the ciphertext blocks across the servers. And it turns out that kind of combining a lot of those tricks together really pays off well and kind of like further minimizing the main bottleneck of this protocol, which is the bandwidth overhead. Well, questions, I guess, is not really true, but like...
What questions?
Yeah?
So I know you focused on the malicious server case.
Yeah.
It sounds like one client can just send a jump vector.
Yeah.
Use some vectors that will get jumped.
Yeah.
One client can just
Yeah. Yes. So what we do is right now is we assume that the clients run in TEs and that they basically... Huh? Yes, the clients use TEs, the servers do not use TEs. So the clients are kind of basically forced by the TEs to kind of like send well-formed messages. But a natural kind of like next question is to say, well, what happens if I actually break a TE? Then like, one client can take down the whole network. But the good thing is that in this case, like presumably this is something that happens hopefully rarely, that we don't break a TE all the time. In this case, we can observe that the protocol kind of like finished with a not well-formed state. We didn't produce output messages even though we had all the data. And at that point, we can fall back to a very slow protocol where we just say, well, great, all the clients, please prove in zero knowledge that all your messages are well-formed. And at this point, kind of like, they will be detected because they will not be able to produce this proof. So this is kind of like the fallback guarantee that we're thinking of if a TE were to break. Yeah?
How does that fallback routine work? If someone breaks their TE, how can they, is this like a secret or something? Or?
So if somebody breaks their TE, then the attack that they would do is...
Like if they have access to the client and everything inside the client, could they produce a well-formed message if they wanted to?
They can produce a well-informed, they can break the TE and behave honestly, but we're fine with that. And I mean, the TE wants you to behave honestly if you behave honestly without.
Behave dishonestly. So they pretend to be honest until eventually they're not be honest. I don't really understand how
So
it works as a detection mechanism.
they can be selectively behave dishonestly based on their own view of what they were about to be sending. They cannot behave dishonestly based on what the other parties are about to send. So this is important. And then what I meant with zero knowledge proofs is like an after-the-fact thing. So like we run the protocol, we realize the protocol produces this garbage sum of arrays thing, which we cannot decode. And at that point, we do the fallback mechanism where now we ask, okay, clients, please explain what you did with a much slower mechanism, which we hopefully only use if somebody breaks the TE to exclude them from the network. Okay? Yeah? That is a very long conversation to be had. For now, we assume that magically happens. We're working currently on like different types of protocols, and they come with different trade-offs. You can do things like dispute resolution from like cryptographic protocols, but it's a there it's like partially a cryptographic question, partially a question about which trade-offs are you willing to make. Do you want to have censorship resistance? Are you okay that some clients may be excluded? So we're basically figuring out right now which of those trade-offs we want to make.
I think maybe the more straightforward answer would be that the clients use Ts, and the Ts make sure that you can't send different messages to different parties. They will at some point see that, oh, you sent like the T proof shouldn't check out at some point.
But you also need to make sure servers see the same commit.
Yes, and we have a mechanism for that, which is like a more interactive protocol of basically there's like a dispute resolution thing. Like if some parties don't see it, they complain, and then we have a mechanism for figuring this out. Again, like, depends on the precise guarantees that you want from a security perspective. If you want that like the protocol produces stuff, but maybe you accidentally excluded some of the honest parties, which is like, a censorship attack, there is one protocol. If you say, I don't want to accept censorship of clients, then there is another protocol which increases bandwidth overhead, but in addition you get kind of like the censorship resistance properties where no client can be falsely excluded. So we have both flavors, and then it's a question of which one do you want to use when. Okay, I guess Mateusz tells you now practical stuff in some direction. Yeah.
All right. Well, never mind. All right, so we've implemented this. The repo is not open source quite yet. It will be probably tomorrow. Yeah, I'm just here to show you that it's quite simple, as you would expect. This is the primitives that you can use to build a protocol using this anonymous broadcast channel. Yeah, just some specific signatures for what you can use to build your stuff. Basically, all that Mark was saying is here. I don't think I should get into like the details of this. TLDR, we have a key additively homomorphic encryption scheme, right? So has the expected functions. You can encrypt, decrypt, and you can aggregate. We have a homomorphic vector commitment scheme that Mark, I don't think, talked about. So this is what we are using to.
This is what we're using to prevent malicious server from misbehaving. So I glossed over it, but
this is why the servers don't have to run TEs, right? Because we have a homomorphic commitment from the clients ensuring that servers have to produce correct openings for the decryption, or will detect the servers that were malicious. All right. So very specifically, we're using it's all lattice-based, basically, frankly, post-quantum, if anyone wants that. Even in case you don't want post-quantum, this is the best scheme to use for this particular implementation. Yeah, we've not had too many issues with it. It's very fast. The signatures are small enough. We're using GPunk for the commitment scheme, which turns out to not add too much overhead. It's actually just invisible. Like all of this lattice overhead is just invisible in the benchmarks. I'll get to that in a second. All right, and one note on the encoding. So Mark touched on it. You can. One of the big problems that we have is how do you specifically encode the messages? How do the clients encode messages into these vectors, because they have to be collision resistant and additive, right? Very important. Otherwise, the protocol doesn't work. The usual things to try would be the invertible loop filter, but it does add a lot of overhead, right? It's like roughly 3x overhead. But we did find the Newton GR trick that seems to work quite well with basically no overhead. It does add a lot of compute overhead. It's something like 5 times slower. But it actually doesn't matter because the bandwidth is such a bottleneck that we can easily increase the computation time by 10x and still not see it in the benchmarks, which is kind of crazy. Right, so at the level of like a service or someone implementing this protocol, this is what you'd see in an application. It's really quite simple compared to what you could expect. And yeah, benchmarks. So The naive way of doing this is not very efficient. Like, this is pretty terrible. So just to explain the table a bit. So we have 3 different ways of encoding the client messages. On the left, we have just an invertible Bloom filter. It's like a collision-resistant vector. We have the Newton-Raphard trick, which is very nice, but does take quite a bit to compute. And we have something we call slot reservation. So this is like a two-round protocol, where in the first round, we use very small messages to just say, I want to be a part of the next round. And I just put like a very small ID in it. And then when we reveal the original output with the very small messages, we can allocate the scheduling vector very efficiently. So there is no overhead here, but it does add some latency. But it's very fast to compute. So just in case that's wanted, you can do it. And yeah, the overhead, this is just like a structural overhead. So we can go, we can have no overhead on the encoding itself, but the total overhead of the protocol is still there because all of the clients have to fit, right? So if I'm a client, I want a 4 kilobyte message, and there's 100 clients. Well, I need 100 times the size, right? This is where this is coming from. There's some additional overhead from the encryption envelope, and that turns out to be around 400 times what you'd want. But thankfully, bandwidth is pretty good these days, so the throughput is not that bad. Okay, a word here. This is what Mark mentioned as the practical tricks to improve bandwidth usage, right? So if we just say, okay, everybody just sends to everybody directly on the links, the throughput is absolutely terrible, right? So this is where we're getting like 50 kilobyte per second, which is not gonna do, or like 100 kilobyte per second. And even increasing the link size doesn't really help that much. We get to like 0.5 megabyte. But if we start using the tricks, for example, aggregation, so we have a separate set of parties that clients send to, that all they do is add the ciphertexts, right? So you don't see any of the cryptography material, just any of the keys at least. You just add the ciphertext together. Then that already improves quite a bit. We can go all the way to almost 3 megabytes per second, basically with 4 gigabit links, which is not like this is standard bare metal networking instances that we're talking about. And yeah, and the CPU overhead is just not here. Like it's not here in the table for a reason. It's just takes under 600 milliseconds to compute even the biggest messages. This measure specifically is for 300 clients concurrently sending 16 kilobytes messages each. So this is like almost 5 megabytes of data coming through. And it takes like half a second to do all the computation in like serially. So this is not relevant CPU-wise. It's just about the throughput and just about the link sizes and whether we can have tricks to optimize the bandwidth usage. Yeah, and I think that's it from me. Yep. Okay. Questions? How many servers do we envision? Probably a lot. So this protocol is quite resilient. Scales very well with servers. This here is for, I believe, 16 servers. I benchmarked all the way up to like 128 servers, and it doesn't really register all that much, especially if you're using Azure coding for disseminating the traffic. It actually improves the throughput the more servers you have. Which is fun. How many servers do we envision? Well, how many honest, trustworthy parties can we find to run those servers? They're not expensive. It's just we need to find people that want to actually run those reliably, long term. I think that's the bigger problem. I think 1632 would be a pretty good thing to aim for. The nice part is that the threshold, the honesty assumptions is that we have like a constant amount of malicious servers, of honest servers. Like if 2 servers are honest, that's enough to secure the network, which is amazing, right? So even with 16 or 32 servers, you're actually pretty good on the security. Yeah.
How do these techniques compare with secure aggregation techniques that have appeared in the literature, like Velo and other such techniques?
So basically, these papers like Willow and OPA paper by Antigone, they do. So, for example, Willow uses a very similar approach with a key additively homomorphic encryption scheme, and OPA does that implicitly. They don't call it like that, but effectively, what they construct is again the same object. They pay quite a lot in terms of zero-knowledge proofs. So what they do is they say, okay, we want to prevent malicious behavior, so we need to kind of like prove in zero-knowledge that a bunch of things are correct and happen correctly. What we basically here say is, well, you know, there's like a lot of the heavy lifting in terms of like, you know, what you would prove to be well-formed, or like, you know, where the zero-knowledge proof kind of like expense comes from is from like, you know, proving that the client sent well-formed messages. And if you assume that the client sent well-formed messages, then with some commitment tricks, you can even ensure that the servers send well-formed messages with like no zero-knowledge proofs, but in a very lightweight way. So that's kind of the route that we took, as you can think of those papers as kind of secure aggregation papers with zero-knowledge proofs. And what we say is we put client-side TEs, and that makes both the clients and the servers a lot cheaper, while only affecting liveness in the worst case, not privacy.
All right. Any other questions? No. Thanks a lot.